All right, everyone, we'll get started. Today, we're going to have a presentation on Kubernetes security, and I've called this an overview and some code. Towards the end, we're going to see actually how we implement some additional, more granular Kubernetes security policies. But broad brush, we're going to cover just the stuff that's built into Kubernetes by default. Here's our agenda. I'll give a brief history of security, and then we'll talk about role-based access control in the context of Kubernetes, and then any host security primitives that might come out of that. And then we'll do admission control, and then pending everything working properly, we'll do some demos. So when I gave this talk the first time, I had this conversation with a friend of mine. I said, hey, I'm going to give a talk about container security. Would you like to come? And she replied with, containers have security, with a question mark. And she wasn't necessarily wrong, right? So we've certainly the container ecosystem do a lot to be better about security. A lot of the containers that you see on Docker Hub or Quay or GCR.io, by default run as root. We can move away from that, but there's also a lot of other things that we can do, limit the blast radius of any compromises that we may have. This is a talk about Kubernetes security specifically. So if you're looking for an overview of Kubernetes, I will talk about some of that, but I do implore you to go listen to the talk, Kubernetes, This is the Way. It's posted on the Parsons website. Kelly's a great guy. He manages Kubernetes deployments all the time. He's really, really helpful. So you should listen to him if you have any questions about Kubernetes specifically. So our history lesson is we used to have clear rules for how to load and manage software. And it started out with, we didn't have security at all. And then we moved to kind of the multi-user environment where we had users and groups, and we limited who had access to root. And that limited some of that blast radius there. Then we kind of moved in the direction of putting things on separate machines, but then we often over-provisioned or under-provisioned those machines. When we decommissioned a server, that server couldn't necessarily be used for something else, just because it didn't have the right resources available to it. And then somewhere along the lines, we started firewalling everything. So we blocked remote access attempts from outside our trusted network. So you couldn't even try to brute force a password or similar. And then we moved into the realm of virtual machines where we, right-sized a hypervisor, and we, loaded it up with RAM, and then we could take smaller virtual machines and kind of, schedule those on all of those much larger hypervisors. The processor vendors actually helped us out a lot there. All of that was managed in the silicon, right? So all of the separation of privilege, all of that was managed in the actual hardware. It marked the appropriate memory pages, so you couldn't necessarily break out of those. And that made it a lot nicer because we could, again, get these big machines and then not really worry about what work we were going to put on them so long as we had that capacity somewhere. And then we eventually decided that we weren't going to do our own security, and we moved to the cloud. And there's, certainly some arguments to be made there about whether or not that's more secure. But what was nice about the cloud was we would only, build and pay for what we needed or what we were using. And it allowed us to spin up our entire infrastructure to like a replica of our infrastructure in the event that we needed to test something. So that was very helpful. And again, if you didn't need the infrastructure, you didn't need that server anymore, you could just turn it off. And then it was the cloud provider's responsibility to manage that and manage all the security updates for that. Now we're kind of in this realm where we're moving everything to containers. And the container ecosystem, I think, is just a good way of deploying and packaging software in a lightweight format. It doesn't necessarily replace virtual machines, but it makes it a lot easier to deploy a piece of software that we write. And when I was kind of running through these slides before, someone pointed out that Docker containers are a thing, but containers exist without Docker. There are other runtimes like CRIO, Rocket, Podman, etc. But I would argue that Docker Inc. made containers more mainstream and made it very easy to use for the purposes of deploying them everywhere, right? So we can deploy on bare metal or in a VM, development or prod, it didn't matter. And then what was really powerful about these was we can run multiple related services on one machine. So if you had a development environment or you had a development workstation, you could spin up multiple replicas of the same application. So if it's a web application, you can spin up the front end, the database, the caching server, and all of that on the same machine. And if you wanted to make a change to it, you could do that locally. You didn't have to wait for someone else to provision you a virtual machine or try to figure out what dependencies were necessary. It was just available. The problem that came with that was we now have the same issue where we have these machines that are quote unquote right-sized, and it would run that application. Well, if we had to increase the capacity of that application, then we were still all tied to that one machine. So orchestrators came along, much like VMware vSphere started handling vMotion and moving your VMs around as it needed to. Orchestrators do the same thing in the Kubernetes context or in the container context. So I have this comment here, orchestrators are responsible for scheduling work for you. And I have M pods or containers over N nodes. So you have some number of pods or containers over nodes. The word pod comes from the Kubernetes ecosystem, where a pod is a grouping of containers that share a network namespace, but a single pod or a pod can contain a single container, and that's okay. So in this talk, I will use the term container and pod pretty much interchangeably, because all of the things that we're going to talk about today can be applied at either the pod level or the individual container level within Kubernetes. And then orchestrators also, brought us the ability to manage work that was transient, so I could move it around if I had a much larger workload and I needed more capacity on a machine. Kubernetes will manage, tearing down the old work and then moving it to somewhere else. That work is ephemeral, so if containers go down or pods go down, then Kubernetes will just go, oh, you needed 5 of these, and spin them back up on a different node. And it also allowed us to tolerate hardware failures. So if an entire worker node fails, it'll start to schedule those on other nodes. But it also allowed us to bin pack. So we didn't have to, again, right size, much like we had these virtual machines that we could now pack onto these hypervisors. And as long as there was capacity in the hypervisor cluster, you could run that virtual machine. Same thing here in Kubernetes. But you might be saying multiple tenants on the same machine. This is in the same operating system, and we've digressed. You might be saying they did what? So at a high level, what we're going to talk about today is the Kubernetes ecosystem at an 80,000 foot level looks like this from a security perspective. You have container, pod, and host isolation, and that is the classic host-based security in the multi-tenant environment. This is the brunt of our talk today. And then you also have API security. So you can say, hey, you can use either what's called attribute-based access control. There's no integration with the kubectl utility, so you can't necessarily modify it without having SSH access to the API server where you can edit that text file. So that's not super useful if you want to have self-service permissions. So Kubernetes went the route of role-based access control, which we will cover today. And role-based access control says, hey, can this subject X perform operation Y on resource type Z? And this is actually integrated with kubectl, so you can go and manage this as long as you have permission to do so, right from within the same tooling that you ordinarily would push other resources and work into a Kubernetes cluster. We'll also touch on webhook authorization, which allows you to have decisions made via an external webhook, and that allows you to have that centralized policy that ABAC had for you. But what's nice about this is it's external, and no, there's no integration with kubectl, but you can have that webhook reach out to other databases and make your authorization and compliance decisions based on what is available to a greater ecosystem instead of a text file. And then typically speaking, everything in Kubernetes has TLS enabled, and all of the machine-to-machine components or machine-to-machine communications use client certificate authentication. So that's incredibly useful from a security perspective. If you don't have the right client certificate, or you don't have a token or a user account within the cluster, you're kind of hosed. And then all of that is encrypted when it gets to the API server. So there's very little chance to eavesdrop on those communications. We will not talk about Kata containers or Firecracker, which allows you to wrap pods in very, very small virtual machines. But that allows you to have that separation of privilege and get back some of what you lost with containers. These are developed by the Cloud Native Computing Foundation and Amazon. They're very, very powerful. They're a little bit difficult to implement at first, but once you've kind of wrapped your head around it, it works. We'll also not talk about network security, but you can imagine if we have ephemeral work, so work that is bouncing back and forth between all of these nodes, it might be getting a different IP address. Kubernetes actually manages what nodes, what pods can talk to one another with network policy, service mesh, and ingress controllers. I'm sure we'll have another discussion on that at a future dates, but not today. Before we go any further, are there any questions? Awesome. So we'll talk about workload security first, and we are going to focus in on what is known as the pod security context. So if you've ever pushed work into Kubernetes, you've probably written one of these manifests, and they typically look like this. So pod security context manages the host-based security of a given pod. So it provides both a pod level at the top arrow there and a container level context. So anything that you specify in the pod level, you can override in the security context of the container level. And all of the options we're going to talk about here today are available in both of those locations, but for brevity's sake, we'll only include the pod level path. And then if you want to use it at the container level path, you can. So workload security. We have these things called privileged pods, and they are useful for managing things like networking, host mounts, and things of that nature. So they're good for controllers. They're good for managing things on the host that you need to manage from within the context of your pod. The caveat there is you greatly reduce the sandboxing of the pod. So much like we didn't necessarily need to have locks on our Tide Pods for a while, some high schoolers thought that it would be a good idea to start eating these, and we started having to lock them up. And then I was looking for Tide Pod memes, and I found this one. This is not true, but this is the kind of person that we're dealing with in the general case. Everything devolves to this level. So if you trust your users too much, then they're going to end up doing something like this. So moving on from there, we have what are called Linux capabilities. Now, these allow you to give fine-grained control to a pod without using the privileged flag. So if you need to do network management, so you have a network controller, and you can specify the net admin privilege. If you need to do file system operations, you can do sysmount. And then there's dozens of other ones, which are available at that link. We won't cover them here today, but really what this is saying is privilege doesn't let us exercise enough restraint with the permissions that we give. So many controllers in the Kubernetes ecosystem are moving the direction of using capabilities. The way that privilege is implemented under the hood is using sysadmin. So if you give sysadmin privilege to a container, you've effectively made it privileged, and you may as well just pass the privilege flag. And if you're writing policy that dictates, hey, you can't set privilege, but you allow someone to set sysadmin, you've failed. You've done the same exact thing. And these are managed in the manifest under these two contexts. So typically what you'll see is a drop all, and then you'll see an add where it'll add back any additional capabilities that you may need. We talked briefly about multi-user environments and having users and groups that kind of provided some of that privilege separation for us, and nothing really ran as root. That's exactly what this is here, right? So these are standard Linux users. If you've ever used Docker and you passed the -u flag, exact same thing. These are specified in the manifest under these three nodes. So spec security context, run as user, group, and FS group. And the FS group key, if you specify that, will create a supplementary user ID attached to your user, and then it will walk any volumes and basically run this command. So that's super nice if you want to limit the privileges of your pod, but you have to go and like chown or chgroup a bunch of data underneath it. There were some very serious performance implications of doing this, because it would literally walk the entire file system and then make those changes. So new in Kubernetes 1.18, they added this FS group change policy at the same level it's in the security context. And you can say either on root mismatch or always, and this will basically only make those changes if the root of a given directory structure does not match the FS group. From a security perspective, we've all heard of SLinux. And I know that in the general case, the first thing that I do when I get on a machine is I type set and force 0. We're all guilty of it, I'm sure. But this allows you to apply an SLinux context to the pod and its connected volumes. And it's specified here as a string under SLinux options. And I got to ask this question, when would you need an SLinux policy for a pod? And there's just a different way of thinking about it, right? Pods and containers are just wrappers around your software. So you're writing the policy for the software running in your pod, not for the pod itself. And that allows you to steal that policy from someone else. So if you have a DNS server that you're running inside of Kubernetes, you can actually steal the SLinux policy from the OS vendor and then apply it here to your workload. I always ask the question, has anyone ever written an SLinux policy? I've only gotten a couple of raised hands, but this is certainly me, and I never run, audit to allow. I just type set and force 0 most of the time. So other workload security primitives, this is non-exhaustive. I listed the link at the end of the presentation on where you can go and look up all of these, but the security context has a few additional fields that you should be made aware of. Allow privilege escalation is an important one. If you're a software developer and you want to gain more privileges, you can pass execve, and if this flag is not set, the Kubernetes will actually allow you, well, the host will allow you to escalate your privileges to something that the parent process doesn't even have, so you can gain more than you probably should have. If you need a read-only file system, I think that one's pretty straightforward and self-explanatory. And then run as non-root says a container cannot run as root, but it doesn't really care what user. It'll just say, hey, this container is not allowed to run as root, and it won't schedule it. This is useful if you're passing a user directive in a Docker file. So you can basically say, hey, I'm going to manage my users in my Docker instance itself or in my Docker container itself. But Kubernetes, I just want you to make sure it doesn't run as root, and I'll take it from there. Don't ask me about Windows options. I've never used them. They are available. You can run Kubernetes on Windows. Kelly may have something to say there. I'm not sure. Kelly or someone on his team may have something to say there. I've never used it. Please don't ask me. Then there's also, you can use other host-based security primitives, right? So if you're familiar with AppArmor or CComp, you can use those as well, but these are not mainlined in Kubernetes or stable, and they're typically run as annotations. So if you go up one level and you go into the metadata key, you can specify one of these, and then if you want to apply an AppArmor policy to a given container, you can specify that here. Same thing for CComp at the pod level, and then that third bullet is CComp at a container level. So the problem with a lot of this stuff is this is all opt-in, right? There's no guarantee that the user will specify any of these keys. So it's kind of a gentleman's agreement. Hey, if you don't need these privileges, I need you to tell me what you don't need, right? And we can't necessarily trust everybody when we're doing that. So we need to talk about policy enforcement. So Kubernetes provides what are called pod security policies, and it enforces these at the API server level. So before your work even enters into the Kubernetes cluster, it will validate that you are meeting this security policy. And this specifies a set of security options that you must present in your pod, or it will kick it back with a security issue or with a security error. Cluster administrators can override any pod security policy, but a given user may not. And PSPs are bound to individual service accounts. So this is useful if you want to, say, prevent someone from mounting a host path volume. You can specify that kind of at the high level or at the base level, and then you can create another pod security policy and then bind it to, say, a service account that is going to do backup jobs. So your cron job running in Kubernetes may be allowed to mount host volumes and may be allowed to run as root, but for any given tenant, you would never want to allow mounting of host volumes. And the reason for that is you may not care if they mount some temporary directory that no one else is going to mount, right? But you probably do care if they mount their run Docker socket, right? That would be very bad, and they could start running containers outside the context of Kubernetes. Kubernetes won't even see it. They're not bound by the same rules and restrictions that Kubernetes would bind them to. And then they can just run arbitrary work. And that's certainly not good. As a word of caution, this has bit me before. Don't enable PSPs by default without writing a good PSP for your control plane. So your API server, your kube proxy, any container networking you may need, those all need PSPs as well, or the cluster will not come online. That's it's pretty awful to troubleshoot and debug, but I've listed at the bottom there a couple of policies provided by the Kubernetes developers. So how do we make this easier, right? So pod security policies are incredibly draconian. But you can template some of the requirements for them. So this pod presets resource allows you to stub out given security policies in the context of a namespace based on a label selector. So you can say, hey, if there's a label that says app Kubernetes name MySQL, you can assign a run as user, and that might be enough for you. But if that label isn't present, then it won't get assigned that run as user. And this is also useful for injecting any environmental information into your pods. So for sake of arguments, you have some secrets that are managed out of band from your work. You may be able to utilize pod presets to inject that information at runtime. There are some limitations. It basically boils down to an if this, then this. So if a pod has this label, then apply this mutation to it, this modification to it. And anytime you have two presets that conflict with each other, it just fails entirely. These are also not enabled by default. They've been around since Kubernetes 1.6, and they've never moved out of the alpha stage. So that's not necessarily a good feather in their cap, right? But pod presets are also nice for governance. You can assign, or this is just a quick note, they're nice for governance. If you need to assign an organizational label, you can specify something like, compliance.parsons.com/team contacts and then specify an email. And that makes it nicer for anyone that's managing your cluster to say, hey, this pod is misbehaving. Who can I reach out to in case they don't know? So are there any questions there so far? Okay, so next we're going to talk about role-based access control. And this is kind of the nuts and bolts of how Kubernetes security works under the hood. And from a role-based access control perspective, you create roles to regulate a subject, that's a user, a service account, a group, to limit a subject's access to resources managed by the API server. Those are defined in two places, either a cluster role, which is cluster scoped, or a role, which is namespace scoped. And you use these two primitives, role binding and cluster role binding, to bind a role to a subject. But the note here, and I'll drive this home a few more times, these are very, very coarse. They're not very granular. So here's some examples of some roles. At the top, you'll see a role on the left and a cluster role on the right. And on the left side, you'll see that there's this namespace field. There's no namespace field on the right side. So this allows you to create a role within a namespace that allows a given subject to, in this case, read any information about pods. So get them, watch for any changes to them, and list them. On the right side, you'll see that's a cluster role, and that's a secret reader. So this allows someone who is bound to this role to read any secrets in your cluster, but not make any mutations to them. Okay. So on the left, at the bottom, you'll see a role binding, and I've bound this role to a user named Brian in the namespace default. So Brian can read any information about pods. He can't create them necessarily, but he can read any information about them in the context of the default namespace. Over on the right, I've actually created another role binding. Now, I could certainly do a cluster role binding here, but what's nice about this is this role binding allows me to generate a standard set of privileges that I'm going to give to users, and then I can assign them in each namespace, but not have the role object itself reside in that namespace. So it's good for reuse. And in this case, I'm giving the user Kelly permission to read secrets in the development namespace. So what you would not want to do necessarily is give Kelly or Brian a cluster role bind for reading secrets, unless you wanted them to be able to read secrets regardless of namespace. So this seems like a lot of pedantry. It seems like it's a lot of extra work, but there's actually a pretty cool pattern here, which is you can, once you've actually applied a role binding, the actual role reference, that lower arrow, that whole section is actually immutable. Kubernetes will not allow you to mutate that after it's been applied to your cluster. So you can create self-service permissions management, self-service roles that you can give to users. So I can give Kelly permission to modify role bindings or create role bindings in the context, or excuse me, to update and mutate role bindings in the context of his own namespace, but he can't change what they're bound to. So if Kelly wanted to give Brian secrets access in the development namespace, he could, but there's no need to bring a cluster admin into the mix. But again, I want to point out, these are very coarse. They don't necessarily specify, hey, you can only read this particular secret. You can only read this particular pods information. And that's okay, and we'll see why that is later. So going back, we'll reiterate, Role-based access control can be stated as this subject can perform this action on this resource type. So a subject is any given service account, user, or group. An action is one of these verbs. So get allows you to get information about the pod. List, you can list pods in the case of a pod. Create, update, patch, etc. And then there's some verbs that only apply to some resource definitions. So a resource here in the statement is any Kubernetes resource, but take note, not all verbs match to each resource, and you can print these by running that command that I've presented. You can't list a subset of pods. You can't list a subset of namespaces. That's probably okay. If you need more granularity than that, my recommendation is to just put those pods or that work in its own namespace, and then you're still bound by the same rules that Kubernetes requires, but you don't need to implement anything additional on your part. And then just as a separate recommendation, unless it's absolutely necessary, my recommendation is to set these two fields in a pod manifest to false. And you can also set that on an individual, and you can set this on the default service account as well, because I'll show you here in just I'll show you an example here in just a second. You can actually get yourself into trouble if you bind the default service account to a given pod. In older versions of Kubernetes, less than 1.10, I think that was 2017 timeframe, the default service account actually was a cluster admin. So every single pod in the entire cluster had the ability to run arbitrary work and mutate arbitrary objects. That's not so great. So just just in case something happens and someone accidentally applies some role binds to the default service account, this is a good way to just prevent it from having any access whatsoever. And then just a couple of tips. When you're creating these roles, you want to create a service account and then bind it to that role. And that allows you to run things like kubectl auth cani with an action and a resource. So if you're a cluster admin, you can actually impersonate another user as you're building these. And you can say kubectl auth cani get pods as Brian or as Kelly or whomever. But again, you typically reserve the impersonate action for cluster level or cluster admin level users. You can also show all your authorized actions within a namespace. You can say kubectl auth cani and then just pass list and then pass a namespace, and that will actually print to you a list of all of the different things that you can do within a namespace. And then I provided this command. This is one that I use pretty frequently when I'm working on role-based access control. So what I'm going to do here is take that. Perfect. So we will run this command, and this will print for me a list of all of the different users, all the different role bindings in my cluster, and then the name of the role that it's binding, and then the subject of it. So in this case, we have this, so we'll come down here, we'll look at this role binding for open policy agents, and it's got a config map modifier. And you'll see the subject is system service accounts OPA. Now, if we actually go and look, you will not see a service account in the OPA namespace other than the default, right? So this default doesn't actually have that permission assigned to it. But there's a little, there's a Kubernetes primitive where you can actually have groups within your namespace, and the system service accounts OPA subject actually corresponds to all service accounts in the OPA namespace. So even though default doesn't have a given privilege or a given set of roles assigned to it, it picks up anything that is presented to it by this system service accounts OPA group. And in this case, it can modify a config map in the OPA namespace. So that's just a little gotcha, and it's something to look out for. And that's what we talk about here at the bottom. But if you're writing these from scratch, you have the system aggregate to edit role, and that contains most of your available permissions. I've listed a link there to where this is actually defined. And then if you can also use a tool called audit to RBAC. This is something that the Kubernetes developers themselves actually maintain. And well, one of them maintains. And this basically allows you to look at the audit log and then pass a user or a subject to it. And it will generate a role for that user. based on what they've tried to do recently and were unable to do so. So one last word of caution about this. This is directly from the Kubernetes documentation, and I felt it important to just literally copy it wholesale here. It says a user granted permission to create pods can read all secrets, all config maps, and impersonate any service account in the namespace, regardless of authorization mode. So what does that mean? That means that if I give someone access to create pods in a given namespace, and there is a service account not tied to that user, maybe it's allowed to go and make changes elsewhere, or worst case, it's allowed to make cluster level changes, they can just bind that service account token to a pod that they create, and now they have permission to execute any API call they want in the context of that pod. That's very dangerous, and it's just something to keep in mind. Any questions there? Okay. So last, we're going to talk about policy enforcement. So troubleshooting policies can be very, very difficult depending on how much introspection you have into your ecosystem. So if a manifest is accepted by the ecosystem, but it doesn't run, and you haven't given the user like explain or the ability to go and get information about why it's failing, well, then they're going to get frustrated and they're not going to want to work with it. And then this is a frustration of mine. Where do I go for a list of those security requirements? And when was that document last updated? So if it's anything like this Xbox, it was last updated in January of 1601. And that's not super helpful to me. And if it's just, if it's just saying fail, 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 I'm just going to start listing tickets in Jira until somebody answers my question. So we said before that we can modify manifests with a pod preset. That's something that you can certainly do. But when I'm troubleshooting something, I don't want to know that some arbitrary mutation is taking place under the hood, right? And in addition, if there's some other policy, some other compliance or security policy, I might want to base that decision on something external to the Kubernetes ecosystem. So I can't do that with a pod preset. And then, we'll pose the question, what if we could guarantee security and compliance, but keep the user informed about how we're doing that? So that's where Kubernetes provides what are called admission webhooks. So this is on the left here. This is the life cycle of an API request. It gets picked up by the API handler. It goes through authentication and authorization. It says, can this user do this using role-based access control? Very, very coarse, right? Then we go into this mutation phase where we can actually modify any object that comes into the Kubernetes ecosystem. So I can take that object and say, oh, they're requesting this user. They're saying they want to run it as roots. I'm just going to mutate it to run as somebody else. Then it goes into schema validation, so it makes sure that is actually still a valid Kubernetes object. And then it goes into the validating phase, which allows you to validate that it's meeting all of your security and compliance policies. So what that means is, the reason we do it in this order is the mutating webhook makes a modification, and then the validating webhook validates it. If we inverted these, it would allow us to mutate after the validation phase and potentially mutate into a state that is not our compliance or security policy. And then just as a pro tip, if you are writing this, or if you are writing one of these and you want to take some action against pods, my recommendation is to do it at the pod level. Request access to all of the pod resources that come through, because the Kubernetes higher level primitives like stateful sets, deployments, daemon sets, cron jobs, replication controllers, all of those different primitives actually make the same API requests that you would make for just pushing a pod through your ecosystem. So if you want to take an action against a pod, there's no need to write it for the stateful set, deployment, etc. You can just write it for the pod, and then anytime something comes through, just do it on a pod by pod basis. It's a little more overhead that way, but it's super useful, and you get all the information knowing that it came from this stateful set, this deployment, or otherwise. But it can be frustrating, again, if you go and mutate something underneath the user and they don't know why. So the tool that we can use for this admission phase is called Open Policy Agent. Now, Open Policy Agent, this is straight from its website. It decouples policy definitions from policy enforcement. So we can define our policy outside of the Kubernetes ecosystem, and then we can we can tell Kubernetes to go get dispositions about a given policy from that webhook. So if you have a pipeline that you're pushing through, you can actually have it, not a pipeline. If you have a resource that you're pushing through your pipeline, and you want to say, hey, does Justin have permission to run a pod in this namespace? You can do that with RBAC, but you can also do with something like this. You can say, it's 2 a.m. Why is Justin trying to push this through, right? Or, hey, Justin's trying to request a given run as user, and he shouldn't be doing that. Or Justin's trying to push through, and that's this third bullet here. Justin is trying to push through a container image that doesn't come from our internal registry. So I'm allowing him to run potentially untrusted images that were not built here in our trusted cluster. This is also useful for specifying the different FQDNs that an ingress can point to. And you can also mandate the user or mandate that a CI pipeline provides this annotation here. So if you must have a team contact label for compliance purposes, because that pod is restarted 1,000 times in the last hour, or it's using way too many resources, you can actually just specify this, and then you'll know exactly who to call. As a caveat, you can only bind to the create, update, delete, and connect operations. And what you'll want to do if you want to bind to a create or an update is bind to both, because you can get into a situation where I can push a pod through as a create operation that meets my compliance requirements. But then if I don't specify the update, I can go back in and update it and mutate it so I can potentially get more privileges or gain more or change arbitrary fields in it. So that could be bad. And then delete is super useful if you want to call out and make a change to some other database. So if you want to reserve a host name for a given pod or something, you can reach out, say, hey, I no longer need this, and then delete it from the database and then remove the pod. That's super nice for that. And then as a quick plug, Open Policy Agent is not Kubernetes specific. You can use this for SSH authentication. You can use this for validation of your manifests outside in like a CI situation. You can use it for really anything as long as you can boil that down to an HTTP API call. So it'll give all that information to the policy engine, and then you move on. So we'll do a short demo here really fast. Hopefully it works. Ask questions as you have them, and we'll walk through what this is going to do here in just a second. Squared away. What we're going to do is we're going to look, I've already installed Open Policy Agent. It's a little outside of the scope. It takes a few minutes to go through, but suffice to say, Open Policy Agent is installed here. So what we're going to do is we're going to show the default Open Policy Agent policy. So I've listed this here. This is straight out of their documentation. And this cluster role binding here exists, and it binds the OPA, well, it's called OPA viewer, and it binds the cluster role called view, to the group system service accounts OPA. So that's any service account, the subject's system service accounts OPA. So that's any service account in the OPA namespace will have this permission. So then we have this role here, and this allows the Open Policy Agent to modify any config maps that are present in the OPA namespace. This is only used in this case, again, this is where the granularity comes into play. This is actually only used to mutate a singular annotation on the config map to say, yep, this config map loaded successfully, this policy loaded successfully. I can also do any arbitrary config map in this entire namespace. So if you have other work here, and this gets compromised, well, then they can go and modify any config map. So again, that's where that granularity comes into play. So then we have another role binding that says, hey, we're going to bind this config map modifier to that same user group. So any service account in this namespace, the same rules apply as before. Create a service, and then this deployment is, and then we'll push through this deployment, which basically just replicates any namespace information into Open Policy Agent. So that's where that cluster view role comes into play. It's actually going and grabbing information about all the namespace resources and then caching it locally so it can make very fast policy decisions. There is a bit of a race condition. This is eventually consistent. So if you make a change or one of these namespaces mutates as a pod is going through in our case, it may not get the appropriate mutation. So just keep that in mind. And then this is the default policy. So it's saying we're going to import data Kubernetes admission, and then there's this thing called main. This is the default policy. And we're basically going to say, hey, if this admission deny down here at the bottom is empty, then we're going to say that it's allowed through. In the case where I give a reason to deny it, it's going to specify this admission. This will hand us back a string. Again, this is all default. This is all straight from Open Policy Agent. So what we're going to do is, so what I've done ahead of time is I have marked up this namespace that we're sitting in, and I've created two annotations on it, one called example.org default UID, and one called example.org UIDs. So what we're going to do in this demo is we're going to push through a pod, and if it doesn't have one of these UIDs assigned to it, we're going to throw an error and not allow it to continue. And we do that by way of this rego policy. So this basically states, hey, here's this deny, and here's this deny set. And if you remember our original policy, that default one, it's calling admission deny. This is the admission deny policy, and it's getting the current namespace that we're trying to push that pod into, or where that pod will land, and then it's getting a list of all of the UIDs as a series of strings. And then in the case where this violators variable is greater than 0, we're going to continue through and we're going to generate this message that says policy violation. You must specify, a run as user from this list for these violators. Now, what does that mean? So this violators set here is a list of any pod name, or excuse me, container names that are in violation of our policy. So what we do is this is how you iterate in Open Policy Agent. You specify a variable name here. In the case where I don't really care what that value is, I can just put an underscore. So I'm going to iterate through every container in our pod specification and see if its run as user maps to one of those UIDs. Now this has to be a function, and that has to do with what is called universal qualification in Open Policy Agent. But if I was going to write this in something like Python, I would say for C in containers, for UID in UIDs, if run as user in their container run as user does not equal UID, add that container name to a set, and then return that set. So if we get any violators, we'll generate this policy violation, and then we'll print to the user that it's a violation. So let's see. Let's go ahead and apply this. Perfect. And then we're going to take this pod here, pod.yaml, which, as you'll see, does not have a security context at all. It doesn't have a run as user at all. We're going to run this. This is just a busybox pod, and all it's going to do is print its ID information, and then exit. So this kubectl apply, we'll run that. And as you'll see, we get an error from the API server saying, hey, you have a policy violation. You have to specify spec containers, security context, run as user from that 2000 and 3000 in these annotations up here for the container busybox. So perfect. That's exactly what we wanted to happen. We've now informed the user that, hey, there's an issue with it, and we will not allow you to proceed. So if we were going to make this compliant, we would have to specify a run as user. So if we say 3000 here, we can say this. We can run this command. Same exact thing, I'm just specifying that compliant pod. And you'll see I've printed the run as user, again, from within the API server. And then this is the actual log from the container running. And that says the UID is 3000 and its GID is roots. So we want to clean that up in a future states, but for the purposes of this demo, that's sufficient. Are there any questions there? Can we do better? Well, I would argue that we can certainly do this differently. And as we talked about before, we don't necessarily want to mutate something from underneath the user, but we may have a case where we want to make an arbitrary mutation to a pod or to a resource. So what a mutating admission webhook is for is to provide not only that disposition, but also potentially something that a patch to the resource that will make it compliant. So you'll often see this used for service meshes, where they'll inject a sidecar container and an int container, and this will allow them to basically inject their service mesh primitives into your work without you having to go and modify every single manifest. Now, the disposition from a mutation hook says, no, you may not proceed with this request, right? That's the false. And that's typically reserved for something went wrong, right? So I couldn't reach out to this backend database. Maybe I didn't have any information to work on or to give you a proper disposition. You can also specify, yep, this request may proceed with no modifications. Or you can say, the request may proceed, but you must make these changes first. Now, the nice thing about this is we can actually instruct the Kubernetes API server to make those changes on our behalf. So we'll see that here. And all we're going to do, the only thing that's different about this is in the case of a non-compliant pod, we are going to mutate it to give it a run as user. So we'll see that here. So what we are going to do now is we're going to go back to our policy, and we're going to so what we're going to do is we're going to specify a mutating webhook configuration, and then we're going to hook all create and update operations for pods, and we're going to send any requests that come through the API server to the service running in the OPA namespace with the name OPA. That's our webhook. And then we're going to tell it to post that resource definition to v0 data Kubernetes admission patches. Well, where does that come from? Well, that comes from our policy. So let's go ahead and kubectl y-f mutating. So we'll allow that to go in, perfect. And then we'll go back to our policy. So our policy has this patches endpoint here. And what this is doing under the hood is this is how you, so first of all, this is how you do OR operations in Open Policy Agent. So I have an is creates, and that looks at the request and it sees if the operation is a creates, and then I have is updates, and then I have is create or updates. And if this, I've actually specified this twice. So I can say if it is a create or it is an update, then this will be true. So the nice thing about these policies is as long as they don't overlap, you can specify a bunch of very minute policy definitions. And if any one of them triggers, then that particular higher level construct triggers. So I use that here in this patches endpoint. So what we do is we see, is it a create or an update operation? Yes. In our case, it will be. And then I call this patches endpoint here, and it generates a list of patches for me. So what that does under the hood is it goes through every container in the request object, and it calls this patch template function. So patch template looks to see if it has a run as user. If it does, we do not touch it, and we do not generate a patch for that. Otherwise, we go and we look and we see what namespace this is going to land in. We grab the default user ID, and then we can generate what's called a JSON patch. This is how Kubernetes manages this. And it's basically, I want to, in this case, we're going to add the run as user, or excuse me, the security context to that pod's definition. And then we are going to add the run as user with the value from that default UID. And it will generate this for every single container in your pod if you have multiple. Unless there is already a user ID there, in which case the validating admission webhook will go and pick it up and say, is this legit or no for our namespace? And then it will marshal it as JSON, URL, or base64 URL encode it. That's just how Kubernetes does it under the hood. And then pass it a disposition as to whether or not it should proceed with the patch bytes in this case. So what we will do is we will rerun those exact same commands that we ran before, but now we have that mutating admission webhook present. So I'm going to, just for grins, we'll reload our policy, even though we made no changes to it. And then we will say kubectl apply to this pod. Actually, we're going to go off script for just a minute. And we'll say sudo -i, we will go OPA. This is the logs, these are the logs that are coming from that admission webhook at this point. So what we'll do is we'll specify our original non-compliant pod now. And you'll see that there was a decision log that was created here. So now our run as user is run as user 2000, and its UID is 2000. So we've mutated this and made it compliant for our cluster. In the case of our compliant pod, it leaves it alone. It's still that same 3000 run as user. Now, again, going a little bit off script here, let's change that pod compliance line. We'll say user 4000. Hopefully this works. Regret this. So if I do this, sure enough, it says, hey, security context for the BusyBox pod does not have one of our valid users. Okay. So really fast, we'll come over to our decision tree over here. So this is the disposition that was created. Oops, sorry, let's stop that. This is the disposition that was created. So I have a policy violation. That's that message that you saw. And then if we come up here, this is actually the document that was presented to us. So it says it's pod. It has these annotations. And then if we come down to there we go. Sorry. The security context run as user, it said it was 4000. So this is the document that was presented to our webhook. And then we just walked the document and said, oh, okay, the security context run as user is not correct. So throw that error back. So cool. Vijaya, you have asked, what best practice challenges do you see in defining regulatory compliance requirements for boundary definition and data and traffic flow between pods or containers? Second, how does attribute-based access control to facilitate conditional access and use affect this? So these are a little orthogonal at this point, or within Kubernetes. But as far as the data and traffic compliance between pods, that would be managed by either a service mesh, probably something with Spiffy enabled, where you can assign tokens to it and it will do mutual authentication external to your pod. So you can guarantee that those two pods are allowed to talk to each other. They don't make that decision. Some higher order function does. And then as far as attribute-based access control, I don't recommend you use it at all. The Kubernetes developers have recommended that you switch to role-based access control. And again, it's orthogonal to the traffic traversing the cluster. This is more used for policy dispositions against the API server itself. Can I run this work? Can I make this modification? Those types of things. That doesn't answer your question. I will be happy to talk more about it. So going back to our slides really fast, we're just about done. I've listed some further reading. If you have any questions about it, most of our talk was in the security context. We're talking about admission controllers, so I've listed those two links at the top. And then if you want to play around with some of the things you've seen here today, you can go to Katacoda, Courses, Kubernetes, and then Playground, and it will spin up a 2-node Kubernetes cluster for you, and then you can try some of these. And then you can also go to the Open Policy Agent documents. I implore you to do so. It's exceedingly powerful capability for doing policy definitions out of band from your software. So if you're writing anything that has access control, right, even your Django apps, those are basically assigned to different groups, and it's not very granular. Your policy definitions in Open Policy Agent can be much more granular than anything that they can be much more granular. And since they're outside of your ecosystem, you don't have to go and release a new version of your software anytime you want to change the way that your access control works. You can just modify this policy with a text document. So armed with all of that, are there any questions? Okay. Well, I will take everyone's silence as either my mic is no longer working and we missed the entire presentation, or that no one has any questions. So thank you all for your time today. I'll stick around for a little while if questions trickle in. And then as always, I will get these posted usually by the end of the week or early next week.